So let's talk a little bit more about our Laplace transform. And as I mentioned, I know that everybody has seen this before in previous classes, so we're not going to go into it in a lot of detail, but I want to just hit the highlights to make sure we're at least somewhat on the same page here. So again, our goal here is we want to make our input, our output, and our system characteristics distinct in our problem so we can represent it in that simple block diagram we saw in the previous video. So what is our Laplace transform? So we can go back to our sort of strict mathematical definition for a minute. So we can say the Laplace transform of some function f of t, so a function in the time domain, is by definition going to be capital F of s. So s is our variable in the frequency domain. And this is by definition for our one-sided Laplace transform equal to the integral from 0 minus to infinity of our function in time f of t times e to the minus st dt, where our s is equal to sigma plus j omega, and of course our j is equal to the square root of -1, so our j is our imaginary number, which means that this s over here is complex. So it has a real and an imaginary part. Fortunately, we're not going to have to deal with this equation directly. Instead, what we're going to do is we're going to use common transform pairs, and that's going to be true for just about everything that we're going to deal with. But let me take a step back and sort of talk about higher level, what are we actually doing with this Laplace transform and why is it worthwhile? Well, let's say over here on the left we have our time domain. So let's say we just sort of have this amorphous area which represents our time domain. And so we have some problem over here. And so this problem is we would need to do some type of calculus to solve it. So for instance, that differential equation that we saw in our previous video. Now over here on the right, let's have another sort of amorphous shape here representing our frequency domain. And of course, these aren't necessarily, the frequency domain and time domain aren't necessarily places in space. These are just mathematical ideas. So what we're going to do is this problem that we have in our time domain, we're going to take this over to our frequency domain, and we're going to be able to do that with our Laplace transform. So oftentimes I'll just abbreviate that L dot t. So now once we're in our frequency domain, we're looking at this same problem, and it turns out that that calculus problem now becomes an algebra problem. So of course, this is in most cases going to be a lot easier to solve. So we can go ahead and, so let's say we solve our problem here in our frequency domain because it's easier now that we have this algebra. And once we solve it, we're going to use another process and we can go this direction and using something called our inverse Laplace transform. And so once we're back in our time domain, of course, now that we've solved our problem, we have our final solution in time. And again, this is just sort of a high level thing. In the next video, we're going to take a look at an example, which hopefully will make this sort of how do we actually apply this process. It'll make that make more sense. Okay, so a couple other things to note as far as resources in the textbook and other things available. So in your textbook, you can see table 2.1, which is on page 28. And so what this has is common transform pairs. And so again, hopefully that's just a refresher, but if you have any questions or if you want to see derivations for any of those pairs, just let me know and I'll be happy to do that. One other thing I want to mention really quick is that in these videos, the page numbers, as often as possible, I'm going to try to make sure I'm referencing the 8th edition of the textbook. In the notes posted on Canvas, the page numbers are shown for the 7th edition of the textbook. As far as I can tell, and unless I say otherwise, the table and figure numbers should be the same. Again, if any of that's confusing, please let me know and we'll try to straighten that out. Another useful table is table 2.2, which is on page 29 of the 8th edition textbook. And so what this has is transform properties. And so we'll talk about some of these as we're working examples throughout this chapter. I'm also going to put up some supplemental info on Canvas. So supplement on Canvas. And so what this is these are some notes from where I teach this material in ENG 301, or at least I have the past couple semesters. So this gives you a little more detailed look into some of these things that we're sort of glossing over. You can also go back and look at some of the videos. I'll either link those or mention those in class so you can find those easily if you want to review a little bit. So first thing, a little more detail on this inverse Laplace transform that we talked about here. So typically when we're doing this inverse Laplace transform, if we're doing it by hand, we're going to be using something called partial fraction expansion. So we're going to abbreviate that as PFE. And once we do the partial fraction expansion, we then just come back to this table of our known pairs. And for most cases, again, we can do that pretty easily. Something else that's covered in this supplemental material, again, whether you want to look at the notes on Canvas or go back to the videos from the ENG 301 course, we have sort of 4 different cases that you might run into. So once you have this solution and frequency, there are sort of 4 different forms that might look like. The first is we might have real and distinct poles. And we'll come back and we'll describe in nauseating detail what poles are, how they interact with our function, all that stuff. For now, if it doesn't make too much sense, don't worry about it. For our second case, we have real and repeated poles. And also, if you look at some of those examples in the supplement, hopefully that'll clear it up as well. Our third case is complex and distinct poles. Okay, so in the supplemental notes, that's as far as I went in terms of detail, but there's actually a 4th case as well that just gets a little more tedious, and that's complex and repeated poles. Okay, so that's all I intend to do in terms of describing our Laplace transform. So hopefully this sort of figure right here in that description gives you a good high-level idea of what's going on. In the next video, we're going to look at an example, and hopefully that will help you get a feel of how to actually use this technique. From there, we're going to talk about our transfer function, and then we're going to get right into analyzing some circuits, and after that, get into some mechanical systems as well.